Okay, so we're integrating this with respect to x. So we leave that pi out there in front, and when we integrate it with respect to x, the big R is just like a constant. So it remains as r squared, and we put an x on it. It's the derivative of r squared x, where r is a constant, which is b r squared. And then the antiderivative of x squared would be x cubed over 3. And our limits now move to the right side. So we're going from negative r to r. And then it's just a matter of plugging in at this point. Plug in our upper limit. So we've got r squared times r minus r cubed over 3 minus, let's put some parentheses, we've got r squared times negative r minus negative r cubed over 3. Change colors here just to kind of differentiate. R squared times r would be r cubed. And that's minus 1/3 r cubed. But let's simplify what's inside of our parentheses before I move on. So r squared times negative r would be negative r cubed. And negative r cubed is negative r cubed, but we're subtracting it here, so that becomes a positive r cubed over 3. And then we're subtracting this whole thing, so it changes those signs. So minus a negative r cubed is really plus r cubed. And minus that positive r cubed over 3 is minus r cubed over 3. So let's put together our like terms first. So r cubed plus r cubed is 2r cubed. And we've got minus 1/3 r cubed minus 1/3 r cubed, so that's minus 2/3 r cubed. So if we express that 2 as something with a denominator of 3, that would of course be 6 over 3. So 6/3 minus 2/3 is 4/3 pi r cubed. Now that should look familiar to you. 4/3 pi r cubed is the volume formula for a sphere. And this is where it comes from. That's how someone figured it out. They didn't just plug in a bunch of numbers and play with a bunch of volumes to figure out that that was the volume formula for a sphere. It came from calculus. Okay, so if it has a radius of big R, that's why the volume of the cube is 4/3 pi r cubed. Pretty neat, huh? All right, so I need you to practice cross-sectional volumes on the worksheet. Oh, no, wait, hang on, sorry. One more example. Let's look at one when it's with respect to y. Okay, so compute the volume V of the solid in figure 4 whose base is the region between the inverted parabola, y equals 4 minus x squared, and the x-axis, and whose vertical cross-sections perpendicular to the y-axis are semicircles. So they're nice to us here, and they give us a visual of what we're looking at. So we've got the parabola 4 minus x squared. We're looking, the base is between that curve and the x-axis. So we're talking about this right here is our base. And then these are our semicircles. They're perpendicular to the y-axis, and they're semicircles. So if we're talking about it being a semicircle, we need the area for the semicircle. So area of the semicircle is half the area of a circle, so 1/2 pi r squared. We need our representation for our our radius. Okay, and look, they give that to us in the picture below that. But let me kind of explain to you why it is the way it is. Okay, so the radius here is equal to the x-coordinate. Okay, it's really the x-coordinate because this length r is the distance from the origin to what we would consider the x-coordinate. So if we use our formula here, y equals 4 minus, and instead of x, we use r because the radius is the same as the x-coordinate. And if we solve that, we get y minus 4 is equal to negative r squared. That negative, when we divide by a negative, that's going to change all our signs. We're going to reverse that order, right? The y becomes negative 4, and the negative 4 becomes positive. And then we take the square root. Usually when we take square roots, we need the positive and the negative, but here we're only considering the positive distance there. Okay, so that's where it comes from. They gave it to you in this problem, but that's how you could figure it out. It's always going to be related somehow to the function. Okay? If these semicircles were perpendicular to the x-axis, then the radius would simply be the y-coordinate, right? If they were perpendicular this way, okay, if that were our radius, well, that is the y-coordinate up there, right? From the x-axis to the curve, that's the y-coordinate, or that would be the radius. But this time they're perpendicular to the y-axis, so that radius is the same as the x-coordinate. All right, so let's plug this in to our volume formula. Okay, let's look at where the volume starts. Okay, they don't give it to us. So actually we need to figure that out. Okay, we've got to figure that out. We've got to figure out where our function intersects with the x-axis. So 0 is equal to 4 minus x squared. So x squared is equal to 4. Take the square root, so x is equal to plus or minus 2. So this one's pretty simple where it intersects. So we are going from negative 2, volume equals the integral from negative 2 to 2. Oops, I didn't put my constant in front. Remember our area formula is 1/2 pi r squared. Well, 1/2 pi is just a constant. Make life easier, pull your constants out in front of your integrals. So 1/2 pi times the integral from negative 2 to 2 of our radius, the square root of 4 minus y squared. And this is with respect to, oh, I screwed that up. This is with respect to y. We're not talking about the x, we're talking about the y. I missed my limits. I messed my limits up. Okay. We've got to figure out where the x is 0. So y equals 4 minus 0 squared. Okay. So y equals 4. And we start obviously down here at the origin. We're going from 0 to 4. So let me fix my limit. And that's why it's very important. I caught that because I realized, oh, hey, I'm integrating with respect to y. My limits have got to be y values. I originally had x values. So even though a lot of times we tend to leave this notation off, we don't really think that it's significant, but if you're in the habit of including it like you should be, it'll help you catch mistakes like that. Okay, I would have gotten the wrong answer if I was going from negative 2 to 2. So let's keep going. We're squaring a square root. Guess what? It cancels. That's nice, right? Makes things easier. Okay, so let's integrate now. So 4y minus y squared over 2. And that's from 0 to 4. So now we can plug in our limits. Plug in 4 times 4 minus 4 squared over 2. And when we plug in 0, obviously both of those have the variables, so they're going to cancel. So let's simplify. We've got 1/2 pi times 4 times 4 is 16. Minus 16 over 2. So that's 1/2 pi. 16 over 2 is 8. 16 minus 8 is 8. This is equal to 4 pi. I'm going to check it in my calculator just to be on the safe side. So 1/2 pi times the integral of, I'm going to go back to the very original just to make sure, the square root of 4 minus x. I have to use x instead of y. squared, comma, x, comma, 0, comma, 4. And obviously that's in decimal form. My answer is in terms of pi, so I just need to check and make sure those are equivalent, and they are. Okay, now what I need you to do is I need you to practice finding the area or the volume of cross-sectional area, cross-sectional figures. So first of all, I want you to practice with the worksheet. Numbers 1 through 4, I want you to do complete without calculator, setup, evaluation, everything without a calculator, and then 5 through 12. Because the majority of the time these questions are calculator active, just because the calculator can't set it up for you. And that's really what they're testing. Do you understand how these problems are set up? So set it up and then use your calculator to evaluate it. The answer key, you will notice, has the integrals. It has the setup, and then it has the answer. So you can check your setup as well. If you're not getting the right answer, you may need to look at the integral and make sure that you've got your limits right, or you've got your area formula right, or you've got it set up right.